But we're going to start talking about velocity here. The first thing we need to do to understand velocity is get an idea for what speed is. People use speed and velocity like they're interchangeable in ordinary life, but to a scientist, they're slightly different. Looking at speed in one dimension, which is how speed really needs to be treated, let's do this by imagining an object that's moving, but it's moving in total darkness. And we can see it only when a strobe light flashes on it. So there's a video camera filming this object, sort of, but we only actually get to see where it is when the strobe light flashes. So once every second we get a snapshot of where it is. So this is what it might look like before it starts moving. It's in complete darkness, and we got a ruler there that apparently glows in the dark, or must be lighted or something. Watch the motion. Every second the strobe light flashes, and you see where the thing has moved to, and it looks like every second it's moving 1 unit farther away. Well, this is a graph that we might use to make a sort of a mathematical or graphical model of what we just saw. If we take time and put it on the x-axis as the independent variable, and the dependent variable is distance, we can make a plot that shows us what does this motion look like graphically. So again, here's side by side, we see the object in motion being filmed with strobe light, and here's the graph that will be a model or a representation of that motion. Watch the motion and watch the graph get built. Well, every time the object moves 1 second, it moves 1 unit of distance farther away. And so we have speed here. Speed, we've already discussed this a little bit in previous discussion. 1/1 is the slope, and speed is the slope of that distance versus time line. So we can think about speed as being that slope. And slope has units of something over something, and it's like meters or whatever this unit is divided by seconds on time, like maybe meters per second or centimeters per second. So let's define speed formally for the first time here, really. Speed, which we're going to call v, even though that really stands for velocity, is equal to the ratio of distance moved, so the change in the position of the object, delta d, or some people say delta x, divided by the change in time during the same movement. That's what velocity really is. Try this. Draw a graph of the speed of the object versus time from time 0 to time 10. Here's a blank graph. This could form the substrate of what you're doing. On a graph that looks like this, remember this is time now versus velocity or speed. I want you to try a graph here. Stop the video and do your best, sketch this out. Okay, here's what we should have found. Since the speed was consistently 1 unit for every second, it never changed. Speed is represented by a straight line that goes all the way across here from 1 to 10. My line's not very straight, not very good at drawing straight lines, but that's the idea. So your graph should look, if you're better at drawing straight lines, like this. Make sure you know why. Why is this flat when the other graph had a slope to it? If you don't know, go back and review, think about it, ask for help. Let's say this was the displacement versus time graph. So this is displacement, this is how far it's moved, versus time. And it's not a straight line anymore. There's some bends in it. This is a little more challenging, but I want you to do the same thing here that you did with the last one. Sketch a graph of speed on the y-axis versus time that corresponds to this object. Here they are, one above the other. Stop the video. Sketch this out. Take your best guess at what this is going to be like. Well, we can see here for the first second that it's going at a constant speed. From second 0 to second 1, it looks like it covers 4 meters in that second. So its speed for that first second is 4 meters a second. So I can draw that as a straight line for 4 seconds. Then it abruptly changes. And then from second 1 to second 4, we can see that it's got a different slope. It's got a different speed during this interval. And it's covering 2 units, it looks like about from 6 down to 4, 2 units in 1, 2, 3 seconds. So 2/3 of a unit per second. So that drops me down to here. And that goes on till second 4. So I can sort of connect the dots here. Oops. Starting at second number 1. And then at 4, it speeds back up again. The object accelerates, its velocity changes. And from second 4 till second 6, which is another 2-second interval, I go from 6 up to 8. So now its speed is at 1 unit per second. So I can jump back up to 1 here and go across to 6. So your graph should look like this if you draw better than me. Again, make sure you know why. If you don't know why, go back and review, and if that doesn't help you, ask for help. Let's say that it wasn't even straight disjointed lines, but it was a curvy looking thing. What's the approximate speed at point A? How could you figure that out? Well, we know that this is a time versus distance graph, or time versus displacement graph. And so slope is what speed is. But slope is not constant here. What we can see, though, is that there's a slope that we can sort of guess at here because that's on a relatively flat spot on the graph. How about point B? The slope is changing here. So we have to sort of pick out what exactly is the slope during that change at point B. And that ends up being the tangent to the curve. So the tangent to the curve at some point is what we call the instantaneous speed, the speed at any instant. So once again, the instantaneous speed, the speed at an instant of time on a graph, is the tangent. That's the instantaneous speed. Let's move from speed to velocity. Speed is just the ratio of distance covered to time. Velocity is a vector, and that's different. Speed is a scalar, it's called. Vectors have size like speed does, but vectors also have direction. So velocity not only tells you how fast you're going, but it also tells you where you're going that fast. Example, 60 meters per second is a speed. 60 meters per second could be any direction on the compass. 60 meters per second east gives you more information. It gives you that direction information. And so that's what we call a velocity. Speed is the magnitude part of velocity. Velocity has 2 parts. Speed is just one. Vectors can be combined in order to find a resultant. Like here's an example. Let's say I have a ball that's moving 3 meters per second, let's say, in this direction. And that ball is thrown by a guy who's riding in the back of a truck that's also going 3 meters per second. Well, compared with the ground, here's what's going on with that ball. If I add these 2 vectors together, I find out that just doubling the length of that arrow tells me what the ball's real speed is. It's 6 meters per second, 3 meters per second, plus the 3 meters per second from the motion of the truck. If the ball was going backwards this way, 3 meters per second, and the truck was moving this way, 3 meters per second, well, when you add these 2 together, you get nothing. So the ball, compared with the ground, just falls straight down, has no speed. Here, they're not going in the same axis at all, and so that makes things slightly more complex. But we can use some tricks from geometry to add this kind of stuff together. Like, for example, if I took this vector here and just kind of slid it over and drew it there, well, this gives me what the speed is going to be. The overall velocity, I should say velocity, the overall velocity is there. Put the arrows tip to tail, and the tail of the first one to the tip of the last one is the added up speed. Well, we can find this kind of stuff. If these are at right angles, it's real easy, actually, because we have some geometric tricks for that, some trigonometric tricks. That's a right angle. We can use a few factors that we know already from geometry classes. Here's one of them, the Pythagorean theorem. We know that if we know this vector and we know this vector, we can square them, add that up, and that's going to be the square of the length of that vector. And that tells us the speed, but it doesn't tell us the whole story. It doesn't tell us the velocity. In addition, we'd have to know what's that? What is the direction? Well, we can find that too using trigonometric functions, sine, cosine, and tangent. Sine, for any angle, is the opposite over the hypotenuse. So opposite side, which would be B, divided by the hypotenuse, which in this case is length C. That's sine. Cosine is adjacent or next to the angle divided by the hypotenuse. So this would be A over C, and the tangent is the opposite over the adjacent. So the tangent for this triangle would be B over A. And we can use these three identities as we need to figure out what the bearing is, or what the heading or the direction is.
Let's try this example. It says here that there's a plane that's flying with an airspeed of 250 miles per hour south. Airspeed means, how fast could it fly if there wasn't any wind at all? And I'll model that with a vector. So I'm going to draw something that's pointing what I'm going to call south here. And it's 250 miles an hour. So if that's my length, I'll just put a little label there, 250 miles an hour. The other factor that's influencing this plane's velocity is the wind. The wind's blowing at 60 miles per hour, and that direction is east. So I'll model that with a vector that's a little shorter, 60 miles an hour. Let's say that's about that long. There's my label, and it's going straight east. Now, the question is, what is the ground velocity, or pilots and people like that call this ground speed, but it's really velocity. What's the ground velocity of the plane? How fast is it going, and which direction is it actually heading if you were looking up from the ground? Well, since both of these factors influence its speed, we can add them together. We could do this graphically. We could just draw a line that goes, a vector that goes from the tail of the first vector to the tip of the second vector, and measure it. We can measure its direction. We can measure its length. But since this is a right angle, it's really easy to do the geometry here. What we're trying to find is this velocity, and that's the hypotenuse, so we'll apply the Pythagorean theorem. It's just equal to the square root of one of the legs squared, so 250 squared, plus the second leg squared, so that'd be 60 squared, and we'll find out what that answer is. Let's grab our calculator, slide that into place here, and I'll put a set of parentheses in there, 250 raised to the second power plus 60 raised to the second power. I'll close my parentheses, and then I'll raise the whole thing to the 1/2 power, which is the same as taking the square root. Oops, not to the 5, but to the 1/2. There we go. And here's what we come up for an answer. When we take the square root, it's 257 approximately miles per hour. So that's the speed. That's the length or the magnitude of that vector. The other thing that we're interested in knowing is, what's that? What's that angle? Where is it headed? Well, remembering our trigonometric functions, we know that the opposite, which is 60, over the adjacent, which is 250 miles an hour, is going to be equal to the tangent of our angle alpha. So that means alpha is going to be the inverse tangent of our ratio, 60 over 250. Well, back to the calculator, we'll calculate that. I will go second function tangent, and that gives me inverse tangent and a set of parentheses. And I just take 60 and divide by 250 inside the parentheses, close it, and my inverse tangent tells me that that angle is about 13.5 degrees. And since we're going southeast here, or east of south, I can specify that on the compass. So there's my answer. Now, this is a problem that's a slightly more complicated one, because we're not going right on the compass directions. It says here a plane is flying with a speed of 280 miles per hour, 35 degrees south of west. The wind is blowing 50 miles an hour at 23 degrees south of east. What's the plane's velocity relative to the ground? Well, you can try this by graphing. One way you can do it is just get a protractor, get a ruler, and very carefully just draw these vectors. Draw this one that's southwest, like that, and then the other one is a little bit shorter, and it's southeast, and then just draw and measure that vector that goes from the tail of the first to the tip of the second one. So that's one thing you can do, and you should give that a try. So stop the video, grab yourself a protractor and a ruler, and draw this and see what you come up with.